Hello and welcome back. So, last week we were looking at convolutional neural networks, what are the operations in neural networks, and we also looked at some of the the operations, the convolutions, how they are done, and some of the more common architectures, so on and so forth. So, in this week we'll start off with looking at how you would code such a thing like CNN in MATLAB, right? So, this is based on this example script provided by MATLAB. I'll just walk you through some of the pieces of the code just to give you a head start and also show you in case you don't understand something and how to look it up and how to proceed. So, it's fairly easy to walk through and create one for yourself. So, this particular script that we are looking at, it tells you how to create a CNN architecture for MNIST digit classification. Okay, so the script itself is available. I will upload the script if it's not. The link to the script or just the script itself so that you can look at it. So we'll start off. So this is again a CNN for MNIST digit classification. So let's look at the data first. So we have to load the data. So MATLAB gives you something called the ImageDatastore object. Okay, you can create one, the object itself. So what it has basically is that it doesn't actually contain the data directly, right? So let's say you have like 10,000 images, right? So you can, and you don't have the hardware to load all of them. So it's not practical to load 10,000 images. You may run out of memory very quickly if you don't have the kind of hardware. So what this ImageDatastore does is that it stores the links to the images. So in a sense, like, it tells you where to find the images. It shows the image directory, the file names of the images that you are using, or the data files you are using, and some meta information about the images. So in this case, size of the image, number of channels in the image, so on and so forth. Okay, so you can create a data store object. So this piece of the code here that I have highlighted right now, it tells you how to create the data store object. So the first line of the code, digit data set path, and so if you look at this, it's full file, and we have all these MATLAB root and all these folder names. Basically it creates a path name, that's all it does. So if you want to see what it is, so let me just, you can run section by section. So I will just run this one section, right? So it's running on the cloud. I guess it's kind of slow, right? So it's done, right? So if you look at the digit data set path, okay, we'll just, if you want to know what it has, you just type it down here, digit, right? So that's it. It has basically the path name to the directory containing the digits data. Okay, so you can actually go put it on your file browser and see where the data is if you want to. So that's what this command does. Okay, full file, it creates the path name, right? And the image data store function, okay, it creates this variable IMDS, which has all the meta information about the data, right? So what does it do? So you give it the path to that directory which has the data, and you ask it to include subfolders. Okay, so basically your organization would be, you will have a main directory where you have a folder or directory if you are using Linux, where you have all the data stores. Okay, so in this case, let's say you have a directory called digits, and inside you have subdirectories which are labeled 0, 1, 2, 3, 4 up to 9, right? So there is a subdirectory 0 which has all the images of digits 0, subdirectory 1 which has all the images of digits 1, so on and so forth. So you would ask it to look at subdirectories also. So include subfolders is true, and label source is folder names. Okay, so image data store can also store the labels. So what does it mean, label source folder names? So you have to name your folder so that it is actually a label for that image. So you know that this is supervised learning. So for every X you need a label Y. So and where do we get that label information from? You can name your directories, subdirectories, so that, or the subfolders, so that the name is reflective of the class of images stored in that subdirectory. So it takes out the it takes up the label data from the folder names themselves. Okay, so every subfolder has to be named intelligently for you to do that. Okay, so if you said, then you can just, these are just objects that you can look at. So for instance, you can do IMDS. Okay, so it tells you what it has. Okay, There's all the labels for each one of them, okay, and it's difficult to scroll, and it has the file names. So you see that the image data store has the following properties: it has all the file names. So it has the entire path. Look at this, there is a folder 0, and inside folder 0 are all these images, right. Each one of them is a image of the digit 0, and there will be a folder 1, so on and so forth. Similarly, it has a label for each one of those images, okay. So there are about 10,000, there are 10,000 images, it has 10,000 labels, okay. So 997 plus 9,997 plus 3, okay. So this is what these two instructions accomplish or commands accomplish in the MATLAB environment. So you need the deep learning toolbox for this. So you just want to look at the data, right. So you just want to make sure that you have the data. So the number of images is 10,000, and then you have a random permutation of 20 of them, okay. Choose a random permutation of 20 of them, and for each one of them you display the images. So that's a very simple enough. So make sure you run section, see how long it takes. So it just displays a different set of 20 images in a panel. So the subplot just creates 4 rows and 5 columns of image display panels, okay. These are small images because each of them are of size 28 by 28. So it's not it comes up very nicely in that panel, okay. So the next task we have to do, like we usually do, is to split these data into training, like here, validation and testing, okay. So there is a function which does that, okay, a method which does that. It splitEachLabel, and you have to give it as input the image data store, okay, because the data store itself has the label information in it. So for every image that you have that is a reference in the image data store, there is a corresponding label, it knows that. So we will say, and we split it in proportion, right. So 0.7, 0.2, 0.1, you see if they add up to 1, okay. So 70% of the data would be training, 20% of the data would be validation, 10% of the data would be testing, okay. And randomize means it will just select 70% of the data at random. So there are 10,000 images, it will select 7,000 at random. If you leave this out, it will just choose the first 7,000 images and the next 2,000 images and the next 1,000 images. So randomize is better because if you want to train, you would like to have a random sample of your data, okay. So if you want to know what these functions do, the easiest way to look them up. So if you are going through this code and some of it appears opaque and you do not know what is going on, easiest way is to just do doc and you do split. Sometimes if you use tab it works, but it does not in this case. Each label, okay. So doc each, okay. So if you do that, then MATLAB help takes you that particular function or method that you are using or whatever. So it gives you different versions of it, right. There are several ways you can use this, it is all listed here. I will not go through them, but the one version we saw is this one which has randomized in it, okay. So you just you can use this to split your training. So this is important because whenever you are doing supervised training, you do need to have a training, validation and testing split, and this lets you do that. And the image data store is a very convenient way of doing it because you are actually not manipulating the images directly, like you do not have them all in memory, you just have the link to the images in the form of file names and all the metadata about the images and their label information, so on and so forth, and this lets you split, okay. So this is how you, if you do not understand any of the functions in there, you can actually do just doc that function. In fact, but if you want to use doc, you have to know the exact function name, okay, or the method name, or whatever that is that you are using, or the construct, right. You have to know that exactly, otherwise you just try help, sometimes that works too. But if in case you are going through the piece of code which they have provided, this is very easy, just do doc whatever and it will pop up the corresponding method, okay. So that's what splitEachLabel does. So we split the data into, so if you are curious as to what it has, so you can just come here and type this at the prompt imds train. Sorry, I have to run this before I do that, so I will just run this. So run section, so let me do that. So it is done, okay, let me see. So it will tell you, so 6,997 more plus 3, so that is like 7,000 data points in the training. So if you look at the testing data, that is because we have set 70% here, You can change this around and just convince yourself that it works that way. And so for instance test, okay, let's do IMDS test. So it lets you see there are 10% of 10,000 images, you have 1,000 images for your testing. Okay. So we have 3 new data stores, IMDS, train, validation and testing. So then the next step is to define the CNN architecture. Again, this is the important step. This is very nice because it actually does most of the layers that you, so every layer is defined by the function and it has its own arguments or method and its own arguments, okay, then you just know what they are. So the image input layer is 28 by 28, right, that is the size of the MNIST data, and it has one channel, right, you can think of it that way. So image input layer, 2D convolution layer, the kernel size of 5 by 5 20 such filters. You have ReLU layer, you know what ReLU is. You have the max pooling layer, 2 by 2 max pooling with a stride of 2. We have a fully connected layer, 10 neurons in a fully connected layer, and this feeds into a softmax layer followed by a classification layer. So what does the softmax layer, you know what, it converts these raw numbers into probabilities, you can think of that way, and the classification layer actually calculates the cross entropy, binary cross entropy cost function. So if you do not know what these things do, that again like I said, so for instance doc, let us do the classification layer, right, doc classification layer. So if you do that, it will show you what exactly it does. So it is a layer that computes the cross entropy loss for multi-class classification. So we are trying to do digit classification 0 to 9, so there are 10 classes, and with mutually, and if you, I am trying to make this full screen, it's risky because then I have to let it come up in the, yeah, for mutually exclusive classes, right. So then it actually infers the output size from the previous layer. So we saw that we have a, so if you go back here to the window, we have a fully connected layer of 10, which is then converted into a softmax. So it knows that there are 10 softmax layers, so corresponding to 10 classes, and it calculates the binary cross entropy cost function. That is what this layer does. So if you want to do so let us say doc convolution 2D layer, so this again tells you what that particular function does and what the inputs can be. So you see that filter size, number of filters, right. So you can come back here, you see the filter size is 5, number of filters is 20, right. So you can do the same thing for ReLU layer, max pooling 2D layer, so on and so forth. So if you run this particular section of the code, you can do run section, it will run it, so it is done. So then you can look at the layers that you have created. So I can just list you, this lists the architecture, your CNN architecture, right. You have an input layer, convolution followed by ReLU. So the ReLU is actually treated as a layer. So you can, but typically you treat them as one, but in most of the programming environments, they are treated as separate layers. Then we have max pooling, fully connected layer, softmax, classification output, right. So this outputs the probabilities. So now if we go down, so we have to set the parameters for training that network. So we have that network, right. So we have to train the network. So again this is passed on like in the form of a, again another variable called options, okay, and you can call this function trainingOptions to do it. So we are using stochastic gradient descent, the maximum number of epochs, we want to run 20 epochs to, in fact one epoch is when you have used all, when you have done backprop using all your data. You have initial learning rate, verbose is false, meaning that it will not have too many outputs. The validation data, you give it the data store that has the validation data. The plots is the training progress, plots will show up, okay. We will run it and we will see what this comes up like. Again, if you want to explore what this, about the different arguments that this function can take, again do doc trainingOptions, it will show you what can be done, okay. And I will run it, I did not run this one, so we will just run this run section, so that works, okay. So here now we are all set. Now we want to train the network. So there is a function trainNetwork, takes the training data as input, right, the layers, this is the architecture and the options for your optimization algorithm. So that is what it does. So we will train it, let us see how fast this runs. I am not sure, so not exactly a fast computer, it runs on the cloud. So we'll see what pops up. So so this window will pop up, right. You can see the number of iterations. It will stop at 1080. So at each epoch, the number of epochs just shows up here, right, epoch 6. So we are doing 20 epochs, if you remember. This is the accuracy of classification versus number of epochs. This is the loss, binary cross entropy loss, that the classification layer computes, and we can see that two different curves, right. The loss is the training smooth loss, and there is a validation loss. You see that they are actually right on top of each other. Similarly here, the validation accuracy and the training accuracy, you can see that there too. So it's running quite fast. We should be done at the 20th epoch. That's the final, yeah. So we're pretty good. So we are almost close to more than 99%. You can see what happens. So it used the CPU. Okay, it works very well on the CPU. So that's fine. The hardware information comes up here. So that now if you're done, then we can close this window, because this just pops up, just tells you how the training progresses. Okay. So it's a very nice information that you can get. So once training is done, okay, the network has the trained weights, net has the trained weights. So then now you want to see the performance on the testing data. So then if you have a network, how do you do the forward pass if you have new data, right? So that's this function classify. If you run here, so it takes all the testing data, runs it through the network, and gives you the output in the prediction. This is a predicted output. And the white test is basically, it tells you the labels for the data in the test data store, right. So this is the ground truth, this is your prediction. Okay. So let's just run this one and section. This should be fairly straightforward. So it's done, hopefully, yes. Then you can look at the accuracy, okay, and you can look at the confusion matrix, both of them using this using these 3 lines of code. So we'll just run that and just check whether this works out fine. Okay. So the accuracy is, okay, the sum of y predicted equal to y test. So this is a logical test. Okay. This is not the equal to sign. So it just considers all the predictions that are equal to your ground truth. So it's either 0 or 1. So you add them up. So the number of correct predictions divided by the total number of test data points, that will give you the accuracy. The confusion chart again is a function with the test labels and the prediction, it gives you the confusion matrix. Okay. So this is the predicted class as opposed to the true class, and you know, if it's off the main diagonal, then those are the false predictions. Okay. So that's what we are looking at in the confusion matrix. Typical confusion matrix should be nice if it's diagonal. Typically it's not. So we have some errors in our predictions, but it's a pretty good performance right there. Okay. So this is just a very simple example of how we can do can create a CNN for, these are small images for MNIST digit classification. You can adopt the same strategy. Of course, each of the important piece of code, there are several, I mean all of them are important in order to make the network. So you just have to, in order to create the architecture, you just, I'm just remove this here, you just create this layers variable which has, you know, every conceivable kind of layer possible. Okay. So if you want to create a deep network, then you just have to put in those commands there, and MATLAB does the rest for you. And you should also be able to configure your optimization algorithm with the right choices. And if you are wondering what the choices are, you just do doc training options, and it will show you what are available, and you can choose the corresponding algorithm. We looked at some of the more commonly used you know, optimization algorithms. They are all enabled in MATLAB. Most of them should be, so you should be fine. Okay. So this is just like I said, a simple example. So in the later weeks, you know, there will be one application week. Maybe we will look at a slightly more complicated architecture. We will look at what they are like. We may try to code them in MATLAB, but demonstration will be difficult because of the size of the data. Another point to note is that you look at how the data was organized. Okay. So they have a root a MATLAB a main directory which has, or the folder which has the data stored in subdirectories, and each subdirectory is named according to its class, and inside each subdirectory is the actual data. Okay. So, when you are trying to solve a new problem, it is up to you. So, this is a canned problem, MATLAB has done all the work for you. But if you have some new data, and if you are trying to, let us say, run a CNN, or for that matter any network through it, or any network on that data, train the network using that data, then it is your responsibility to create these folders. Okay. So, you have to curate the data yourself, that is a essential part of coding deep learning algorithms. Just make sure the data is clean, nicely organized, because once you have them organized in this fashion, then you can exploit the existing methods and functions that are in MATLAB, right. Nothing prevents you from writing your own data store, writing your own code to load one image or hundreds of images at a time and training your network with it. I mean, that you can do that too, but this is very convenient if you use the MATLAB data store, and for that you have to organize your data in this fashion, right. So, make sure that your subfolders or subdirectories are named according to your classes that you have for supervised training, and then and then make sure that all the subfolders are or in one fixed place from which MATLAB can upload the data sets, right. So, and of course, you have to curate them, separate the data and all that. So, that is a lot of hard work. Most of the time that is what takes up a lot of your time. Okay. So, this is how we start off this week. Now we will look at, we will be looking at transfer learning, again hyperparameter optimization. We will also look at one application in how CNNs can be used for medical image analysis, brain tumor segmentation specifically. Okay. So, thank you.